In this lecture, we continue our discussion with cache memories. We start our discussion by looking at how cache misses can be reduced through more flexible block placement strategies compared to direct mapped cache placement. In a direct mapped cache placement, a memory block maps to exactly one location in cache. As compared to that, in a fully associative cache placement, a fully associative cache placement allows memory blocks to be mapped to any cache location. That is, in a direct mapped cache, I have only one line in cache corresponding to a memory block. Okay. In a fully associative cache, all lines in the cache can hold any memory block. In a set associative cache, corresponding to a given a block can be placed in a set of cache lines. So, in a set associative cache allows memory blocks to be mapped to a set of cache lines. So, in a n way set associative cache, I have n alternatives for placing a memory block. Okay. So, I have n alternative cache lines into which a memory block can be placed. How do I get the set location corresponding to a block of memory? The set location is given by block number modulo the number of sets in the cache. So, how do we get the block number? So, as if we remember, a memory address is divided into two parts. One is the block offset and the rest is the block number. So, block number is given by by all those bits of the memory address which is not the block offset. So, the least few bits are for the block offset, the remaining give the block number. So, block number modulo the number of sets in cache. So, that is given. And how do I get the number of sets in cache? If I have, let us say, n lines in cache, then and if I have say 4 ways, if I have a 4-way set associative cache which consisting of n lines, then n lines divided by the number of ways 4. So, n by 4 gives me the number of sets in cache. So, what will be the set location corresponding to a block in memory? Block number in the memory, block number in the memory modulo the number of sets in the cache. In order to find the desired block, all tags of all lines in the set must be searched simultaneously. Why? Because any line in a given set is equally potential, can potentially hold my block in memory. So, therefore, for all, because how do I get my desired line? How do I get my desired block? So, what do? I compare the tag corresponding to my memory address with the tags of all the lines in the set, and this search is done simultaneously, and whoever matches the data corresponding to that is the desired data. As compared to that, in a fully associative cache, the block may be placed in any cache line entry. Okay. In order to find the desired block, the tags of all lines in the cache must be searched simultaneously. So, in a set associative cache, I only have n alternative lines in which a memory block can be placed. So, therefore, because I have just n alternative lines, I have to search the n tags simultaneously to find desired data. Now, in a fully associative cache, all lines in the cache can hold my data. Therefore, all tags of all lines must be searched simultaneously to find my desired data. Now, let us take a toy example. So, we want to find the location of memory block number 12 in a cache with 8 lines. So, I have a small cache containing 8 lines and I want to find my memory, memory block number 12 in that cache. So, in a direct mapped cache, I have exactly one line that can hold. So, and which will be that line number 12 modulo 8, because I have 8 lines, I have exactly one place for memory block number 12, and that line is given by 12 modulo 8 equals to 4. In a two-way set associative cache, in any one of 2 lines in the set 12 modulo 4. Why 12 modulo 4? Because in this 8 line cache, because it is two-way set associative, number of sets is given by 12 divided by 8 divided by 2 equals to 4 sets. I have 4 sets in this two-way set associative cache, and so which set among these 4 sets will hold my memory block 12? 12 modulo 4, and 12 modulo 4 is 0. So, if we see in this diagram, in the direct mapped cache, we see that this line number 4 is the home for memory block number 12, and we match the tag corresponding to that. I need to match just one tag, that of line number 4, to find whether block number 12 is in cache or not. Corresponding to the set associative cache, we said that set 0 is the home for block number 12, and both the lines of set 0 can hold this block number 12, and therefore, I need to search both these tags simultaneously together to see which one contains my desired memory block, that is block number 12. And for this case, we saw that this line of the first set holds my data, desired data. Now, we come to the fully associative cache. For the fully associative cache, any one of the 8 lines can hold the data. Okay. So, therefore, I need to search all my 8 tags in simultaneously to find if my data is there in cache. Okay, my desired data there in cache. Now, after searching for the tag, I have found that this line number 7 actually has my desired data. So, continuing with the associative cache example, I have 8 lines, and we can see here that I have 8 lines, and these 8 lines can be considered to be a one-way set associative cache. In a one-way set associative cache, I have just one place for each memory block. In a two-way set associative cache with 8 lines, I have 4 sets with 2 alternative places for each memory block. In a 4-way set associative cache, I have 2 sets and I have 4 alternative places for each block. Okay. And in a fully associative cache, I have just one set with 8 different possibilities for the memory block. Now, we take another toy example to show how higher degrees of associativity are actually able to decrease cache miss rates. Consider 3 small caches. Okay. Each cache is of size just 4 line and it has 1 word per line, and memory block accesses are in sequence 0 followed by 8 followed by 0 followed by 6 followed by 8. Okay. Now, I have cache 1 is direct mapped, cache 2 is two-way set associative, and cache 3 is fully associative. Now, the line number corresponding to memory block 0 is given by, for the cache 1, for the direct mapped cache is given by 0 modulo 4. 4 is the number of lines, 0 modulo 4 is 0. For 6, it is 6 modulo 4, that is line number 2. So, the home for memory block number 6 is line number 2. The home for memory block number 0 is line number 0, and the home for memory block number 8 is line number 0 again. Corresponding to the two-way set associative cache, I have 2 alternative two different sets in which the each block can be placed, and we see that block number 0 goes to 0 modulo 2 or set 0. So, I have two sets, set 0 and set 1, it goes to set 0. Block number 6 modulo 2 also goes to set 0, and block number 8 modulo 2 also goes to set 0. So, now what happens for the direct mapped cache? For the direct mapped cache, we see that firstly when block 0 is accessed, I have a cache miss. The cache is initially empty. So, I have a cache miss, and then block 8 is accessed. So, block 8 also goes to line 0 and I have a cache miss. Now, when block 8 is brought into cache, block 0 has been replaced. So, block 0 is not in cache when it is accessed here. So, this is also a cache miss. For line number 6, for block number 6, line number 2 is the home. Okay. So, because 6 is accessed for the first time in line number 2, this also results in a cache miss, and when 8 is accessed again, then the home for 8 is 0. Previously 0 is currently in the cache. So, again when block number 8 is accessed, this memory this block number 8 is not found in line number 0, and therefore, again there is a cache miss. So, all my accesses result in a miss in my direct map cache here. Corresponding to my two-way set associative cache, what happens again when memory block 0 is accessed, it is accessed for the first time, it goes to set number 0. So, in my two-way set associative cache, all my blocks map to set number 0, right, and I have two alternative lines, two possible places in which I can place my blocks in set number 0. So, now what happens? Firstly, when 0 is accessed, I put it to the first place in set 0, and I bring it into the cache. There is a cache miss, because initially the cache is empty. Then 8 is accessed. When 8 is accessed, I put it into the second alternative second place in set 0. So, this one memory block number 0 remains in the first place in the first line of set 0, and in the second line of set 0 I bring in memory block 8. Then when 0 is accessed again, my first line of set 0 still contains block number 0. So, now I have a hit. Here, and then what happens when block number 6 is accessed? When block number 6 is accessed, I need to replace somebody. So, before block number 6 is accessed, the first line of set 0 contains memory block 0, and the second line of set 0 contains memory block 8. So, now when 6 is accessed, I have to replace one of these among 0 and 8. We will see later how we do this replacement, but for the time being let us assume that I arbitrarily replace memory block number 8 and put in memory block number 6. This obviously results in a miss, because this was the first time memory block 6 was accessed. Now, after this 8 is accessed again, and now I have just replaced memory block number 8 with memory block number 6 in the second line of set 0, and therefore, memory block number 8 is currently not in cache. So, when memory block 8 is accessed here, it again results in a miss, and now I replace memory block number 0 with memory block number 8 and bring memory block number 8 into the cache. So, here I have just one hit. So, whereas in the direct mapped cache all my accesses resulted in a miss, I have one hit in this two-way set associative cache. Now, when I have a fully associative cache, all my lines can hold data. Okay. The data the memory block can be placed in any of the lines. So, firstly 0 is accessed, I put in line 0, okay, there it results in a miss being the first access. Then 8 is accessed, I put in this line number 1, it again results in a miss because 8 is accessed for the first time. When 0 is accessed for the second time, 0 is currently there in cache and therefore, this results in a hit. And then when 6 is accessed for the first time, this results in a miss and I put it in line number 2. And then when 8 is accessed for the second time, it again results in a hit because it is there in line number 1. So, we have 2 hits here. So, we see that a fully associative cache is able to further reduce the number of misses. So, now we will look at how set associative caches are organized. Now, we will consider the case for a 4-way set associative cache. So, let us consider a memory address here. This memory address has a block offset, it has 8 bits for indexing, okay, and 22 bits for the tag bits. Now, these 8 index bits are used to find the set in the cache. So, if I have 8 bits for indexing, the total number of possible sets in the cache will be 2 to the power 8, okay, or I will have 256 different possible 256 0 to 255 256 different possible sets in the cache, and each set will have 4 lines. So, for example, let us assume that this index, the value of this index has resulted in this location, this set location, and therefore, for this set I have 4 alternative lines. Here is one line, this is the second line, this is the third line, this is the fourth line. Okay. Now, any of these 4 lines can hold my data. So, how do I find is my desired data there in cache, and if it is there in cache, which one of these lines hold my data? So, this will be found by matching with the tags, this 22-bit tag line. So, now what happens? These 22-bit tags are matched using comparators. So, there are 4 comparators corresponding to this, the tag corresponding to the line comes over here, and it is matched with the tag that comes to this. So, this tag is matched with each of the tags in my lines, and if it matches and if the data is found to be valid, then I get my data. Okay. Suppose whoever matches will hold my data. Now, so how do I get my actual output? I get it through a multiplexer. Okay. So, this will tell me that whether I have a cache hit or a cache miss, because this is going to tell me that if any one of these lines are 1 or not. So, when will any one of these lines be 1? If I have valid data which matches. So, I have a tag match. So, if I have a tag match, I will get a 1 on these lines. Now, if I have a 1 on these lines, I will use a 4 cross 1 multiplexer. So, 4 cross 1 multiplexer, and these will be my select lines to choose one of these data inputs. And so, whoever is 1 over here, corresponding to that, the particular data input will be chosen, and the correct data will flow from this line to the output of the multiplexer, and we will be able to fetch the data, that the desired data from my cache. So, we see that the cache is accessed through indexing. The 4 comparators match all tags of the set in parallel. A 4 cross 1 multiplexer is used to choose from 4 potential members of the set. As associativity increases by a factor of 2, that means I go from, let us say, from 2-way set associative to 4-way set associative, or from 4-way set associative to 8-way set associative, what happens is that the number of tag bits increases by 1. Why does this happen? Because when my associativity increases, the number of sets reduces by a factor of 2. So, when associativity increases, so I instead of having 4 alternative places to in a given set, if I had a 4-way set associative, now if I make it a 8-way set associative cache, I will have 8 alternative lines corresponding to any given set. So, for if the cache size remains same, the number of sets in cache reduces by 2. So, therefore, the number of index bits reduces by 1 and the number of tag bits increases by 1. So, fine, the next point is that the number of comparators double. Why? Because the number of lines in a set double. The number of lines in a set doubles. So, the number of comparators will also double. The size of each comparator and multiplexer will also double, because my tag bits increase, the tag bits increase. So, the size of the comparator also increases. Now, if it goes from 4-way set associative to 8-way set associative, the size of the multiplexer increases from 4 cross 1 to 8 cross 1. So, the size of the multiplexer also increases. Therefore, the choice among direct mapped cache, set associative cache and fully associative cache depends on the cost of a miss. So, what did we see? That we saw that when my associativity increases, I have a decrease in the number of misses, my hits increase. However, there is a cost in implementing this associativity. We saw that as associativity increases, number of comparators, size of comparators, size of multiplexers double. Size of all of them increase, number of comparators double, now the comparator sizes increase, the size of the multiplexer doubles. Now, so the area cost corresponding to this implementation becomes very high. Along with that, there can also be certain increase in the hit time. Why? Because just assume that we had a direct mapped cache. In a direct mapped cache, it will require just one comparator. There is one line in which my block can remain, and therefore, therefore, what will happen is that I will just compare with that and get my data. Now, I have to in parallel go through many comparators. The size of these comparators are bigger, because the tag bits are bigger, and then it has to go through a second level of multiplexer to get my desired data, right. So, this all of them that multiplexer will also have a delay. So, the delay corresponding to the comparator, the delay corresponding to the marks may increase. Along with that, I have to go through 2 levels of logic. So, one more level of logic at least. So, therefore, time of access may also increase. So, I have a trade off between the reduction in miss with respect to the cost of implementing associativity in terms of both area, hardware cost as well as time. So, block replacement policy, as we did in the example, as we saw in the example, that when for example, in a 2-way set associative cache, I will just go back to this example once. In the 2-way set associative cache, consider this 6 here. Before this 6 was accessed, set 0, the 2 lines of set 0 contained memory block number 0 and block number 8. Now, when 6 was brought in, I replaced this memory block number 8 in line 1 of set number 0 and put 6 in it. So, we at that time I said that I replaced this memory block number 8 arbitrarily, But what is the algorithm that I used for replacing memory block number 6, memory block number 8 with memory block number 6? So, this is what is the question we are looking at, block replacement policy. In a direct mapped cache, I have no policy. There is no choice, so hence no policy. In a set associative cache, we first prefer non-valid entries. So, if I have a non-valid entry, I will if I have a non-valid entry, I will directly use that and replace that, because anyway that cache location, that cache line contains non-valid data. So, I will replace it. Otherwise, I will choose among the entries of the set. Otherwise, I have this case here that memory block number 0 and memory block number 8 is in line number 0 and line number 1 of set number 0, and whom to replace. The policy that is typically used is least recently used. So, what is least recently used policy? Choose the line which was unused for the longest time. Now, in the above case, if we now go back, we will see that in the above case 8 was accessed in time step 1 in time step 1, and 0 was accessed in times, if this is time step 0, 1, 2, 3, 4, in time step 1 8 was accessed, in time step 2 0 was accessed. Now, in time step 3 when 6 is accessed, 8 is the least recently used, because it has been used at the longest time backwards. So, we choose the one which was unused for the longest time. The other option is to choose randomly. Least recently used is typically mostly used. Random has some advantages we will look at later. Multi-level caches. Now, with respect to single level caches, we have said before that we have multiple cache hierarchies. Now, we will talk about them here. The primary cache or level 1 cache in multi-level caches is attached to the processor. It is small but fast. Added to that, we have a level 2 cache which services misses from the primary cache. It is typically larger in size, but also slower than the primary cache, however, being much faster than the main memory. So, the main memory then services L2 cache. So, what hierarchy do I have? I have the processor, then from the processor I have a small primary cache. Typically, these are separate data and instruction caches. Then basically, I have a combined much bigger in size L2 cache. These are L1, these both are L1, the L2 cache, and this is then attached to the main memory, which is much bigger. Now, in more high end machines, we also have 3 levels of cache. Typically, L1 or L2 are on chip, sometimes L3 cache is off chip. In typically L3 caches are off chip. Now, we will take an example on the use of multi-level caches. Particularly, we will see how multi-level caches are able to reduce miss penalties. Let us consider a CPU with a base CPI of 1 when all references hit the primary cache. So, cycles per instruction is 1 cycles per instruction is 1. So, 1 cycle instruction execution when all references hit the primary cache. The clock rate is 4 gigahertz, miss rate per instruction is 2%, and so 2% of all the instructions miss the primary cache, and I have the main memory access time. So, time to go access the main memory and get data is 100 nanoseconds, and first we will consider the case when I have just one primary cache. So, what is the length of the clock cycle? I have a clock rate of 4 gigahertz. So, the length of a clock cycle is 1 by 4 gigahertz equals to 0.25 nanoseconds. So, what is the miss penalty? So, the miss penalty will be given by miss for the penalty that for one miss is 100 nanoseconds. So, in terms of clock cycles, it will be 100 divided by 0.25 nanoseconds, which is equals to 400 clock cycles. So, 100 nanoseconds to access main memory, 0.25 is 0.25 nanoseconds for one cycle. So, 100 nanoseconds divided by 0.25 equals to 400 cycles. So, when just see that when I hit the primary cache, if I can execute one instruction in one cycle. Now, if I have to go to the main memory, then I incur 400 cycles of penalty. The good thing is that only 2% of these instructions miss the cache, right. So, what will be the effective CPI? The effective CPI will be 1 when I have a cache hit plus. So, I went to the cache, I saw that there is a cache miss. This will happen in only 2% of the cases, or 0.02. So, for all these 0.02 or 2% cases, I will incur 400 cycles of miss penalty. So, what will be the effective CPI? 1 plus 0.02 into 400 equals to 9 cycles. Now, let us assume that with this, along with this cache, we have added a L2 cache. Okay. The L2 cache has an access time of 5 nanoseconds. Okay. To get to the L2 cache, I require to get to the L2 cache and get the data, I require 5 nanoseconds. Now, the global miss rate to main memory is 0.5%. So, the number of the percentage of cases for which I miss the primary cache as well as the secondary cache, means the L2 cache, is only 0.5%. Now, the miss penalty with the L2 cache is given by how much? So, 5 nano, the miss penalty with the L2 cache hit, miss penalty with L2. So, primary cache has missed and in the L2 cache I have a hit. So, what will be the penalty? The penalty will be 5 nanoseconds divided by 0.25 nanoseconds. So, 5 nanoseconds divided by 0.25 nanoseconds equals to 20 cycles. So, therefore, primary miss with L2 miss. So, when I have primary miss with L2 hit, I will have it will be 20 cycles. When I have a primary miss with L2 miss, what will be the extra penalty? The extra penalty will be 420 cycles. Why? Because 400 cycles will be to get to the main memory and 20 cycles to get to the L2 cache. So, the total penalty when there is a primary miss with L2 miss is 420 cycles. Now, what will be the effective CPI? The effective CPI will be 1 when there is a hit in the primary cache plus 0.02 into 20, because 2% of my instructions miss the primary cache. So, 2% of 2% into 20, this many times I will have, and L2 cache access. Out of these, so 2% of the times I will go to the L2 cache, okay, because I have a primary miss. 2% of the times I will have a primary miss, I will go to the L2 cache. For that, I will have a overhead of this. Now, out of this, accesses to the L2 cache, 0.5% will result in misses on the L2 cache, and for each of those times I will have to go to the main memory. So, 0.5% or 0.005 into 400 cycles will be the effective cost. So, the total effective CPI becomes 1 plus 2% of the times I I miss the primary and go to the L2, and 0.005 times I miss the L2 and go to the main memory. So, the effective CPI will be 3.4. Now, the performance ratio without and with the secondary cache will therefore be 2.6. So, with the L2 cache, the processor is faster by 2.6 times. So, when I add the L2 cache, my effective CPI reduces from 9 to 3.4, and therefore, my processor is 2.6 times faster. Now, multi-level cache design issues. So, the focus of the primary cache is to minimize the hit time, because I expect that each time I go for executing an instruction, I will go to the cache and have to fetch. So, I will try to minimize the amount of time I require to access the primary cache and get data. So, what is the focus of the L2 cache? The focus is on low miss rate. I want to avoid going to the main memory access. Why? Because we saw that only one cycle was for hit into the primary cache. Around 5 times was the hit with respect to the primary cache. Around 5 times was the cost of going to the L2 cache, and was 100 times was the cost of going to the main memory if I have to go to the main memory. So, hit time has overall less impact for the L2 cache, because why? Because I go to the L2 cache only when I have a miss on the primary cache. The result is that L1 cache is usually smaller, because I want to access it fast, and to get that I will have a smaller than a single level optimally designed cache. So, if I have a single level optimally designed cache, I do not have multiple caches. With respect to that, my L1 cache will typically be much smaller. Why? Because I have the support of a big L2 cache. I want the L1 cache to be small and make the access times much lower, much quicker. For the L1 cache, block size will also be smaller compared to the L2 block size. Why? This is also that if the block sizes are larger, my transfer times for the block becomes higher. So, lower the block size, lower are the transfer times. So, I will prefer a lower block size for the L1 cache. Also, because my L1 cache size is smaller, so block size will also be smaller in turn. For more advanced CPUs, for example, out of order CPUs, currently whatever we were studying were in order CPUs. So, whatever instructions whatever machine instructions are placed to it, they execute in order sequentially. So, in out of order CPUs, the CPU has the ability to find independent instructions and execute out of order. So, what happens? Dependent instructions wait in reservation. So, I have an instruction, subsequent to that I have other instructions which depend on my current instruction, but after that I also have a few instructions which are independent of my current instruction. So, those independent instructions can continue, and I will have reduction in cache misses. So, in cache misses, if I have to wait for cache misses, my dependent instructions will wait. So, in out of order CPU can execute instructions during cache miss. How? Dependent instructions will wait on the reservation station, and independent instructions will continue their execution. Effect of miss depends on program data flow as well. Now, how the program data means what instructions are accessed after what. So, each program has a control and data control flow graph. Now, depending on that depending on the control, the data will flow, the flow of data through the program is going to vary. Depending on that, the sequence of instructions being executed is going to vary, and cache misses in that case becomes harder to analyze. And the way to do that is to simulate the whole system for more time constrained, more performance centric systems where the demand on performance, predictability on performance becomes very critical. We need to simulate the whole system sometimes to get a measure of what will be the penalty of misses corresponding to the execution of a program. Misses also depend on the memory access patterns, the algorithm behavior. So, and the compiler optimizations for memory access. So, today's compilers do different types of optimizations to improve cache hit rates and reduce the number of misses. We will take an example to show how compiler optimizations can be used to improve cache hit rates. Now, we will take two problems, the first of which is as follows. Consider a 4-way set associative cache consisting of 128 lines with a line size of 64 words. The CPU generates 20-bit address of a word in main memory. Determine the number of bits in the tag, index and offset fields. So, I have a 4-way set associative cache consisting of 128 lines with a line size of 64 words. The CPU, so with a line size of 64 words. So, first thing that comes to mind is that if the line size is 64 words, the block size in memory is also 64 words. That means, the number if I have a word addressable memory, the number of words, the number of bits required to access a word becomes 2 to the power 6, because 64 equals to 2 to the power 6. So, line size of cache equals to block size of main memory equals to 64 words or 2 to the power 6 words. So, the number of offset bits in the main memory address becomes 6. We get the first result for the offset. Then, so the total number of bits for the tag and index fields within the 20-bit address. So, I have a memory address of 20 bits. I have already said that 6 bits are used for my offset bits. So, the number of bits used for my tag plus index field will be 20 minus 6 equals to 14 bits. Now, the number of sets in cache now will become cache size divided by the number of ways. The number of sets in cache is cache size by number of ways. So, we said that that my cache contains 128 lines. So, cache size is 128. I have a 4-way set associative cache. So, number of ways is 4. So, the number of sets in cache is 128 by 4 or 2 to the power 7 by 2 to the power 2 equals to 2 to the power 5, or therefore, I have 32 cache 32 sets in the cache. I have 32 sets in the cache. So, the number of bits required to index the cache will be given by 5. So, I have 5 bits in my index field of the main memory. So, the number of tag bits is given by 20 minus 6 plus 5 equals to 9, 6 bits for my offset, 5 bits for my index. So, 20 minus 6 plus 5 is, so 9 bits in the tag field. Now, we take another example. A CPU has a 32-bit direct mapped cache with 128 byte line with 128 byte block size. So, block size is 128 byte. So, line size is also 128 byte. Suppose A is a 2-dimensional array of size 512 cross 512 with elements that occupy 8 bytes each. So, consider the following two code segments P 1 and P 2. So, before going to the code segment, just let me reiterate, I have a 32 kilobyte direct mapped cache. So, 32 kilobyte direct mapped cache will mean, so what will be the size of the cache? 32 into 10 to the 2 to the power 10. So, 2 to the power 5 into 2 to the power 10. So, 2 to the power 15 bytes is the size of the cache, and I have a block size of 128 bytes. So, 2 to the power 7 is my block size, and I have a 2-dimensional array of size 512 cross 512 of 8 bytes each. So, what will be the total size of my of the array? 2 to the power 9 into 2 to the power 9 into 2 to the power into 2 to the power 3. So, 2 to the power 21, 9 plus 9 plus 3. So, 2 to the power 21 bytes is the size of my data. So, the size of the array is 2 to the power 21 bytes. Now, we come to these two code fragments. Consider the following two code segments, P 1 and P 2. So, in P 1 what do I have? I have two nested arrays. So, the first goes from I equals to 0 to I equals to 512. The second goes from j equals to 0 to j less than 512 j plus plus, and I access x equals to. So, I just sum up all the elements in the array here. So, x equals to x plus a I j. In P 2 I have the same I and the same j, the only difference being that I do x equals to x plus a j I. That means that this for this array I access the array row wise, one row at a time. Okay. So, I equals to 0, for I equals to 0 I first go for with all j's, then I equals to 1 I go with all j's from 0 to 512. So, I access one row at a time. In this case I go column wise. Why? Because I do x equals to x plus equals to a j I. So, first I access j 0 0, then I access then I access a, first I access a 1 0, sorry, a 0 0, then I access a 1 0, then I access a 2 0, finally I access a 512 0, and then I go back to a 0 1, a 1 1, a 2 1, a 3 1 up to a 512 1. Then I go to a 0 2, a 1 2, a 3 2 up to a 512 2. Then I go to a 0 3, a 1 3 up to a 512 3, and so on. So, I access this array column wise. Now, P 1 and P 2 are executed independently with the same initial state, namely the array A is not in the cache and I j x are in registers. Let the number of cache misses experienced by P 1 be M 1 and that for P 2 be M 2. So, find the values of, so I want to find the cache misses for P 1 and P 2 when I execute P 1 and when I execute P 2. So, how do I find that out? So, I have a 32 KB direct mapped cache with 128 byte block size. The size of the array is 512 cross 512, 8 bytes each. P 1 accesses the array row wise as we just discussed. So, block size is 128 bytes. So, the number of data elements in each block becomes 128 by 8 equals to 16. So, my one block or one line contains 128 bytes, and I said that each data element is 8 bytes. So, the number of distinct data elements in each block is given by 128 by 8 equals to 16. Then the number of blocks required to store all the data will be given by, so what is the total number of elements I have? 512 cross 512. Okay. So, the number of blocks, and I said that, so how many elements? The number of elements are 512 cross 512, and in each block I can store 16 elements. So, the number of blocks that will be required to store all my data is given by 512 cross 512 by 16, that is 2 to the power 9 into 2 to the power 9 by 2 to the power 4. So, 2 to the power 18 by 2 to the power 4, which is 2 to the power 14, and 2 to the power 14 is equals to 16384 blocks. Now, I am accessing for P 1. For P 1, I am accessing the elements row wise. So, what happens? when I accessed A00, I incurred a miss and I brought that block of 16, I brought the block of 16 bytes to the 16 elements to the main memory. I brought in the block of 16 elements. Now, this 16 elements, what does it contain? A00, 01, 02, 03 up to 015. Okay. Now, if we see if we just go and look back at the code for P1, we see that I first access A00, then I access 01, I access 02, I access 03 up to 015. So, there will be a miss for 00, but then for from 01 to 015 there will be no misses, because all these data has been brought into cache during the first miss on A00. So, the number of misses will be equal to the number of blocks as accessed. So, all blocks are required to be accessed at least once, and there will be one miss per block. So, therefore, the number of misses will be 16384. Now, however, P2 accesses the array column wise, as I said. I access A00, I incur a miss, then I have what I have brought into cache is A01 to A015. But what do I access next? I access AJI, that means I am accessing A10 next. A10 is again not in cache, and therefore, there will be again another miss in the cache. So, basically if we see all the accesses to the cache will result in misses. So, M2 will be the number of misses will be all the accesses will result in misses, and it will be given by this value, which is 512 cross 512, that means 2 to the power 9 cross 2 to the power 9 or 2 to the power 18. So, this is equals to 2 to the power 18. This will be the total number of misses. So, M1 is 2 to the power 14 and M2 is 2 to the power 18. With this, we come to the end of this lecture.